Hey guys, today I will be explaining the physics quiz for the CA and term 3 week 2. Okay, so let's start right away. Question 1. Which of the following are the results obtained in Rutherford's experiment? Select all that apply. Okay, so this experiment is basically, I don't have a diagram, but it's in the book. They basically emitted a line of radiation, okay, and it interacted with the thin foil of gold. Okay, so what happened is that Rutherford discovered that the structure of the atom is not as what they thought with the other experiment, where they thought it was like that pudding, where it's a sea of electrons in a positive medium. No, it's actually a nucleus of an atom is positively charged. They found out that. And most of the mass of the atom is concentrated in a small heavy nucleus. Okay, so they discovered that there is a small core called a nucleus, and it is positively charged. So, and most of the mass of the atom is concentrated in a small heavy nucleus. So that nucleus makes up most of the mass of the atom. Okay, so yeah. Which is the following? Okay, so this is the same as the question 1. As we said, nucleus of an atom is positively charged. Most of the mass of the atom is concentrated in a small heavy nucleus, like the previous question, and most of the atom is empty space. Okay, so what happened in the experiment when he shot it at the thin foil of gold? Some of the electrons. Wait. Okay, so sorry. So some of the particles were shot back directly. Some made it through, and some were some made it through in a straight line, and some bounced off into different directions. So these different directions of the particles bouncing off made Rutherford realize that the atom is empty space, because most of the particles went through the atom, while the others they hit the electrons and neutrons, and okay, so when they hit them, they went back. They were shot back directly, and the others were shot in different directions. Anyway, this is just memorizing. If you want to know more about it, check the book. So again, most of the atom is empty space. The nucleus of the atom is positively charged, and most of the mass of the atom is concentrated in a small heavy nucleus. This is what the experiment deduced. Right, now the next question. Which of the following are the nuclides of the same element? Okay, so I just want to explain something quickly. This is an easy question, but I want to explain something specific. So nuclides, maybe some of you haven't seen that before, but nuclides are basically this. You see this? Yeah, I'm sure you've seen it in chemistry or physics. All of this make up a nuclide. This is a nuclide. Okay? This is a mass number, while this is atomic number, and this is the chemical symbol for the elements. Okay? So all of these make up sorry, it's messy now. All of these make up a nuclide. Okay? So, okay, let's go back. So, of the same element. Okay, so when we see the same element, nuclide of the same element, we know they are referring to isotopes. And isotopes are elements that have the same atomic number, but different mass number. Okay? So yeah, that's it. Now they're asking us which of these are isotopes. So forget the mass numbers. We'll look at the atomic numbers, because they have to be the same. Okay. So here it's 15, here it's 32, so it's wrong. Here it's 10, so it's wrong, because if it's 10 and 15, it's different numbers. 30, of course, wrong. The only one left is the one with 15. See, they have the same atomic number, which is 15, which makes them isotopes. All simple stuff. All stuff we took in chemistry. Question 4. Which of the following nuclides have the same number of neutrons? Okay. So to find out the number of neutrons in a nuclide, let's take this for example, Mg, magnesium. So 24 and 12. The mass number is 24 and mass number is 24 and the atomic number is 12. Okay. Now they want the neutrons. Before we do anything else, the mass number is usually makes up nucleons, which are basically protons plus neutrons. It's a sum. Okay? While atomic number makes up the number of protons in this nuclide. Okay? So it has 12 protons and this is 24 nucleons. Okay. So since this is protons plus neutrons and we have protons, we don't have neutrons. We're trying to find it. So it's just 24 minus 12. Anytime you want to find neutrons, you just want to subtract mass number by atomic number, and then you get neutrons. Okay. So now they're asking us to compare between all of these elements, which of them have the same amount of neutrons. Okay. So here it's 24 and 12, so 12 neutrons. Okay. For carbon, it's 12 and 6. 12 minus 6 is 6. So not same as 12. And for this third one, sodium, 23 and 11. 23 minus 11 is 12. 12 is equal to 12, so it's correct. Well, this is wrong. Aluminium, it's 25 minus 13, you get 12 also, so it's also correct. All of these have the same amount of neutrons. Neon has 13 here, because 23 minus 10 is 13, so it's wrong. So the only correct ones are this, this and this. Okay? So yeah, that's it. Which of these will be enough to protect against the flux of beta particles? Select all that apply. Okay. So I'm sure you guys know about alpha, beta, and gamma. So here they're asking about beta particles and how much they can penetrate. Okay, so let's list them off. Alpha, beta, and gamma. Okay, alpha can only is the worst one at penetrating. It can only pass through air. Okay, it can't even pass a thin sheet of paper. Beta, on the other hand, can pass through thicker masses. But still, if it gets too thick, it can't pass. So both alpha and beta can stop at specific obstacles. Okay, now for gamma, it's a special case. Gamma cannot be stopped by any obstacle. Maybe there are obstacles like lead and water that can stop it, but they not stop it, but they can reduce it, reduce the speed, or at least reduce the amount that's passing through, but it can never truly be stopped. So gamma can never be stopped, but alpha and beta can be stopped. Okay? So the thinnest one is the alpha, which is the worst at penetrating, second one beta, and the last one gamma, which is the best at penetrating. Gamma, by the way, is the radiation emitted from the sun. Anyways, let's look at beta. Okay, so what beta can pass through? Okay, 1 centimeter of lead or lead, whatever. This can actually reduce the speed of gamma. So okay, lead. Only 1 centimeter of lead can stop is enough to stop beta. And 20 meter of air That's also enough to stop beta. And 10 centimeter of aluminium. Okay, so again, it doesn't really matter on what the material is, it matters on the thickness. Okay, so for example, lead can reduce gamma, but at a specific thickness. It has to be really dense and heavy and really thick. But for for beta, it doesn't need to be really thick. It just has to be 1 centimeter, because beta is not as penetrative as gamma. Now 20 meter of air is also enough, and 10 centimeter of aluminium. I just memorize this. This needs to be memorized. And yeah, 1 sheet of paper, of course not. That can stop alpha, but not beta. Beta can penetrate that. 5 centimeter of air, that's too small. While the others are all enough. Memorize this. Which of these will be enough to protect against the flux of alpha particles? Okay, so again, like I said, alpha can only pass through air, but any other object at any thickness, no matter how thin it is, it can block it. So 1 sheet of paper, 1 centimeter of cardboard, 1 millimeter of aluminium, 1 centimeter of lead, 10 centimeter of lead, sorry, they're all more than enough to stop alpha. Okay? So yeah, that's it. So just memorize it like this. Only specific things at specific thickness can stop beta, but for alpha, everything except a certain thickness of air. Okay? So yeah, that's it. Again, all of this, it has to be memorized. It's not really any understanding it. Which of the following correctly describes the properties of photons emitted during radioactive decay? Select all that apply. Okay. Okay, so photons. What are photons? Photons are particles that make up light. They travel the same speed. So the same everything. Okay? Because photons are what make up light. Alright, so they are very fast. Okay? So let's remove this. So remember, photons make up light, or the particles that make up light. Okay, so they're asking of the property the photons emitted during radioactive decay. Okay, what is radioactive decay? It is when a nucleus that has a bunch of protons and neutrons gets a bit too unstable, so it has to get rid of a few particles, of a few neutrons and protons to stabilize it a bit. That's what decay means. Radioactive decay. Just think of it as kicking out the excess charges. Okay? So this is radioactive decay. It can, there are many types: alpha decay, beta, and gamma. Okay? So now, it's good. Okay, they are referred to as gamma radiation, because gamma is, anyway. So yeah, photons are the same as gamma radiation. Okay, and what I mean that just now, photons in radioactive decay is basically gamma radiation. Okay. And their ionizing ability is just about 10 ion pairs per centimeter of air. We'll look at this in another question, so we can memorize each value for each of the particles, alpha, beta, and gamma, because they all have different ones. But this is for gamma. Gamma has 10 ion pairs per centimeter of air. Okay, but we'll look at this later. And they pass in straight lines through uniform matter. Remember, they pass in straight lines. Okay, that's it. Again, all of this has to be memorized. Okay. Which of the following correctly describes the properties of photons emitted during radioactive decay? Select all that apply. Okay. Wait, what? What's up? Minutes. Okay, something was going on with the question. Anyways, question 8. In Thomas's model, the atom is conceived as a collection of tiny electrons dispersed in a positively charged uniform medium, resembling raisins in a pudding. Okay, so this was the one I was talking about earlier, about the experiments and medium. So this was proven wrong. So this is wrong. Okay. Earlier, like a long time ago, Thomson made a model for the atom, where they thought it was a sea of positive. It was not sea. It was a positive medium, and there was a sea of electrons, negatively charged particles. Okay? So these tiny electrons were dispersed in a positively charged medium, so it looked like a cookie or raisins in a pudding, as described here. So that was what Thomas thought the atom looked like, of what the model was for a while, until I forgot his name, but someone came and proved it wrong. Okay, so now for question 9. The chemical symbol of silicon atom is 2814 silicon. Okay, so here they're asking for the number of nucleons in the nucleus of the silicon atom. Okay, so they're asking for the number of nucleons. What was nucleons? Nucleons was protons plus neutrons. Okay, so we're gonna have to get the protons, which we already have, 14. Okay, plus the neutrons. How do we get the neutrons? We subtract the mass number by the atomic number. So it's 28 minus 14 equals 14. So 14 plus 14 is 28. That's the nucleons. The number of nucleons. Okay, for question 10. Consider the nuclear reaction shown below. Fill in the blank. The value of x is... Okay, they want x in the equation. Let's write it down. Okay, so what we can see here is this is a nuclide, and this is a beta. Remember, beta, okay, let me just show you guys quickly. Alpha, this is the symbol. It's helium 42. This is alpha, okay? Beta is 01E, okay? For gamma, it's just Y. I don't know how to draw it, but there's this, I think it's like this. Anyways, it's a Y. But for beta, it's 0, 1, and E over here, like in the equation over here. Okay, so now we know it's a beta plus decay. Okay, so now that we know that, we can say the value. Okay, it's not really important, sorry, not really important to know, but just for extra information. So 12 and 7 makes up XC6 plus 0, 1, E. Okay, they want us to find X. Since this nuclide here make up these two, we can just add them up. 6 plus 1 is 7, so that would make 7. So what should X be to add with zeros for them to be 12? So X plus 0 equals 12. X will be 12. So 12 plus 0 is 12. So X is equal to 12. Okay? So whenever you see questions like this, you just add the small 1 minute. I'll do it again. I'll zoom in. Okay. So when you see questions like this and they ask you to find, for example, a value, you just add them up So this is the equal sign, imagine it as an equal sign, and this is the answer. You just add up the small numbers over here and add up the small numbers here to make up the nuclide over here. That's it, that's the whole idea behind it. Wait for it to load. Okay, so for question 11, consider 3 isotopes of hydrogen, 3H1, 2H1, and 1,1. Okay, drag and drop the correct isotope of hydrogen to its corresponding nuclear composition. Okay, so this is just simple stuff we took in chemistry. Okay, so here they're asking us to drop the isotopes of hydrogen in one of these boxes. Okay, so they gave us the first one proton and 1 neutron. Okay, all of them are 1 protons, and now we just need to find which one is 1 neutron. Is it this one? 1 minus 1 is 0, so no. Is it this one? No, 3 minus 1 is 2. So, and here's 0. So no way, it's 1 neutron. Is it this one? 2 minus 1 is 1. Yep, it's this one. So for the first one, it's the H21. Okay, and yep, that is it. Okay, now for the other one is 1 proton and 2 neutrons. All of them 1 protons. Now you just have to find the one with 2 neutrons. Like we said here, we found out this was 2 neutrons. And over here, 1 proton, 0 neutrons. 1 proton and 1 minus 1 is 0. So 0 neutrons. So you just have to manually look, and it's easy. That's it. Simple math. And then for parts B, they want us to compare the mass of each one. Obviously, the one that has the most particles will be the heaviest, while the ones that have the least will be the lightest. And here we can see the lightest one being the one with the 1,1, and the one in the middle is 2,1, and the heaviest one is 3,1. Okay, that's it. 12 minutes. Complete the following diagram to describe Chadwick's experiment setup. Drag and drop the correct answers from the box. Okay, so this is Chadwick's experiment. This guy was the person who proved, what was the name? What was the name? Yeah, Thomson's. He proved Thomson's experiment wrong. Model wrong about the reasons the positive medium will see electrons. It's all wrong. How did he find out it's wrong? Let's look in. Now, this is a source that emits radiation, the alpha particles. So we know the source that emits radiation is alpha particles, so we immediately put it here. Okay. Now, for the second one, once the radiation hits beryllium, okay, what happens? A neutral charge escapes, which are the neutrons. That is what Chadwick discovered. What are these neutral particles? Neutrons. This was how neutrons was discovered. Okay. So once the neutrons were released, they hit the wax, the paraffin wax. So once they hit it, they basically what happened was the neutron was heading towards when you go smaller, when you go all the way to atomic levels, the neutron will hit the proton. Okay. So once it hits the proton, it will knock the proton out. That is why protons are shot outwards. Okay? So in the experiment, we realize the source is alpha particles. Once the source interacts with beryllium, neutrons escape, and once the neutrons interact with the paraffin wax, it's messy. Anyways, once it interacts with the wax, it knocks the protons out. That is why they escape here, over here. and the detector detects the protons. This is the experiment which led to the discovery of the most famous neutral atoms, particles, neutrons. Okay, question 13. An atom of iron, 5626 Fe, is neutral. Fill in the blanks. A. This particular nuclear species having specific values of Z and N is called a nuclide. Okay, so like we said with the X and A and Z, all of Fe make up a nuclide. With the numbers, they all make up a nuclide. Okay. Now for part B, a neutral nuclide has 26 protons, 30 neutrons, and 26 electrons. Let's check. Okay, so for protons, yes, it has 26 protons. So protons is 26. Now let's look at electrons and neutrons. Okay. Now, for electrons, and it's always equal to protons unless there was a charge, a minus or plus. Unless there was a charge, the charge would affect the number of electrons. If it was negative, if it was a minus charge, the number here would add up to the electron. If it was a plus, it would subtract from the electron. Okay, but since there was no given charge here, so we just make the electrons equal to the protons. So it's also 26. Now, for the neutrons, again, we subtract 56 minus 26 is 30. And indeed, we got the same amount of values. That's it for question 13. Now for question 14, same atom, iron. The atomic number of this nuclide is 26 and its mass number is 54. Okay, so remember, mass number is always up and atomic number is always down. That's it. Okay, mass number make up the nucleons, which are the protons and neutrons, while the atomic number are the amount of protons. That's it. Okay, so the atomic number is 26 in this case, and the mass number is 54 in this case. Okay, that's it for this question. Now moving on to question 15. Which of the following quantities are the same for neutral atoms of two isotopes of the same element? Okay, back with isotopes. Again, we said isotopes, the properties of isotopes is that they have the same atomic number. Okay, since they have the same atomic number, they would have the same proton number, since atomic number is basically how much protons is in this nuclide. Okay, so these are correct. Mass number, no. Isotopes have different mass numbers. Neutron number, no. And the number of electrons, since protons and electrons are usually equal, so yes, this is also correct. Okay, look, how do you know it's when electrons and protons are equal? They say neutral atoms, so there's no charge. That's why we can immediately deduce that electrons is equal to protons. But if they say a positively charged atom or a negative, then electrons would be wrong. Okay, but here they said neutral, so it's correct here. That's it. Okay, anyways, moving on to question 16. Let's determine whether each statement is describing the electron, the proton, or the neutron. The particle is negatively charged, electron of course, electrons are negative, and the particle is positively charged, protons, particle is neutral, neutron, and particle moves around the nucleus, electron. Okay, let me just draw it out so you can memorize it. This is the electron. Okay, and in the center, the nucleus, which is made up of the protons, which are positive, and the neutrons, which are neutral. Okay, so this is basically the normal structure of an atom. The electron is usually orbiting, okay, around the nucleus. So it's the only one moving around, but then the protons and neutrons are in place. So the particle, the particle moves around the nucleus, yes, electron is the only one that does that. Okay, neutron, as we said, is neutral, protons positive, and electrons negative. Okay, that's it. And if you can't memorize this, just remember protons is positive because P is positive. Protons is P, positive is P. So that's how I memorize it. And for neutron and neutral, it's a basically line. N and equal N, neutral, neutron. While the last one, which is electron, is just negative. That's it. Memorize it like this. It's the easiest way to avoid any confusion in the exam. Okay, so this is what I was talking about earlier, the penetration capabilities of each one, of each particle. Now, we'll need to compare and describe the penetrating power of each radiation. Let's start with alpha. Now, alpha, we can immediately know, since it can't pass the paper, it stops here. So once it stops at something as thin as paper, we know immediately that it's alpha, because it's the worst one at penetrating. So alpha is here. Beta, it's basically in the middle, because it can penetrate some stuff, but it stops at a specific thickness. Okay? Specific thickness. Okay, so it won't pass through the book and move on to lead. It can't. Okay? Now for gamma ray, so beta is here. Now for gamma ray, look, it passes through all of them, because gamma cannot be stopped. It can penetrate almost everything. Okay? That's it. Match each statement with the type of radioactive decay it describes. It is a helium nucleus, alpha decay. Okay, like the symbol that I shown you before, alpha is helium, He, with 4 as mass number and 2 as atomic number. Okay, this is alpha. Memorize it like this. It's always the same number, 4 and 2. Now, for beta, we said it's so 0, 1, صح? Yeah, 0, 1, E. E is basically electron, since beta is negatively charged. So just memorize it like this. E is electron. Okay? Now, for the last two, which are these, they're both gamma. Okay. Now, it is a photon. Gamma is photon. That's why in the previous question we said that it's the same as gamma radiation. And now for the last one, it has a least ionizing effect. What is ionizing? What is ionization? It is basically, think of it like this, the nucleus, okay? Made up of protons and neutrons, is made up with electrons orbiting it. Okay? So now, we'll compare all of them, alpha, gamma, and beta. Now for alpha, it has the most ionizing effect. Why? Because it has a 2 positively charged. It's 2 positively charged. So it can attract the electrons and push it out. Basically, ionization is basically kicking the electrons out. So it doesn't even have to be close to kick it out. It just has to be at this distance. And it can immediately pull the electrons out. That's for alpha. It has the most ionizing effect. Now, for beta, it can just it's basically the median. It's basically what's called. It's between alpha and gamma in rates of ionization. It has to be a bit closer, but still doesn't have to touch it immediately. It's for beta. It's negatively charged. So that negative charges will attract. Negative charges will basically, wait 1 minute. Okay, sorry, so I didn't mean they attract each other. I meant as beta goes on, it loses its charge. like as it goes on. So that will make the electron, it will grab the electron closer, so eventually kicking it out of the orbit. Okay, so yeah, that's it. Now for gamma, which is y, I don't know how to draw it. It doesn't have a charge. Gamma is zero charge, so it doesn't have any pull or push effect. Like it can't attract or like gain charge, lose charge. No, it has to directly hit the electrons to kick it out. Like directly, they can't pull it or push it. No, they have to directly interact. That is why gamma has the least ionizing effect. Okay, that's it. Question 19. An unstable nuclide emits radiation in an attempt to become more stable. This is known as radioactive decay. Like I said, when in the nucleus protons and neutrons are huddled up, when they're too much, it becomes unstable nuclide, right? So they need to become more stable, and to become more stable, they have to do it by a process called radioactive decay, which is basically kicking out some protons and neutrons. Okay, so decay just basically means like kicking out, like I said in the other question. Okay, for question 20 now. Fusion occurs when two light nuclei fuse together to form a heavy nucleus. Okay, yeah, just memorize this. This is just a definition. Fusion is basically when two nuclei, they're light, okay? So they fuse together to form a heavy nucleus. It's just 1 + 1 = 2, basically. All easy stuff. Memorize this as a definition, and you'll be good. Remember, two nuclei fuse and form a heavy one. Basically, you're adding 1 kg plus 1 kg, both light. You add them up, it will equal to 2 kg. Okay? That's it. An alpha particle is released by a nucleus of an unstable atom. What happens to the nucleus's atomic number? Okay. So they want for the alpha particle, which we said is helium 42. It's released by a nucleus of an unstable atom. So this is going through alpha decay. What happens to the nucleus's atomic number? Since it kicks out kicks out the protons, it will decrease by 2, since they have to. Since alpha has 2, it will decrease by 2, okay? And to the nucleus's mass number, it has 4, so it will decrease by 4. Whatever number the alpha has, which is always 4 and 2, the protons will decrease by 2, which is the atomic number here, and the mass number will decrease by 4. That's it. Okay. Now here is beta plus decay. Alright. So over here we saw the 0 and 1, صح? So we know that this is the beta, okay? But we need to see the sign. It's positive here, so it's plus decay. So beta plus decay. Okay, and over here they're asking for the y. What is y? It is a positron. What's a positron? Positron is basically anti-electrons, since they are electrons but positive charged, and basically positive electrons. That's positrons. Memorize it like this. It's they're usually in the beta plus decay. When it's plus, it's positron. Okay, always memorize it like this. So this is a positron. All right, since it's plus. There's other types called beta minus decay, but we don't have that right now. Okay, so now for C, the value of x is 12. Again, like I said, we add them up. 6 plus 1, sorry, you can't see it. 6 plus 1 is 7, and x plus 0 equal 12. So x will be 12. That's it. Okay, consider the reaction shown below. They're asking for, okay, y. They're asking for the value of y and the value of z. We can see here that it's a fusion reaction, since these two nuclei are fusing to form a heavier nucleus, to have a nucleus, okay? So they're asking for the value of y over here, and it says it's 2, and the value of z is 4. Why? Let's see. Let's get z first, because it's easy. Now let's add them up. 2 plus 3 will be 5. Sorry, equal to 5. And 1 plus 1 will equal to 2. Okay? So z is 5 and y is 2. Now, oh yeah, sorry, they meant this y over here, not this one. My mistake. This is gamma aslan. Anyways, so we'll realize that y is 2, but z is 5, but it says 4, right? What the thing is, we forgot about this one, which is no, never mind, it's not better. It's the opposite. Anyways, so what we'll do here, okay, so back to the question. So these two add up to make a nuclide that's 5 and, sorry, I wrote it on the wrong side, 5 and 2. Now we want to make it into this, right? Now let me just erase some. Okay, now z plus 1 needs to be equal to 5, and y plus 0 needs to be equal to 2. So y will be equal to 2 because 2 plus 0 is 2, and z plus 1 z plus 1 needs to be equal to 5. So z is just equal to 4, since 4 plus 1 will equal to 5. So that's why z is 4 and y is 2. Okay? Now for the second one, I feel like I didn't explain good, so I'll just explain again. So these two add up to form a nuclide, 5 and 2. Okay? Now this is equal to this, okay, which is x zy plus 1 0 n. Okay? So z will add up to 1 and y will add up to 0, right? We want the y now and z. Okay, so to equal this, the one we got, the value we got, okay? So y plus 0 equal to 2. Y plus 0 equal to 2. Y will be equal to 2, since 2 plus 0 is 2. Now, for z plus 1 equal to 5, z will be equal to 5. 4. Z will be equal to 4. So 4 plus 1 equal to 5. That's it. Now for the other ones, again, this is the fusion, because we're adding them up to form a heavier nuclei, and the particle X is an alpha particle. Asking about this one. Why is it an alpha particle? Because it's 4 up and 2 down. And whatever has 4 up and 2 down, this means it's alpha. Doesn't matter if it's helium or whatever element. If it has 4 up or 2 up and 2 down, then it's an alpha particle. Okay, that's it for this question. 1 minute. Okay, for question 24, memorizing. Radioactive materials should always be securely stored when not used. Material that is best used for lining the box in which radioactive materials are stored is lead. 10 centimeter walls of this metal will completely stop alpha and beta radiation and reduce gamma radiation to 10% of its initial value. Okay, like I said, lead is the best kind of metal sorry, is the best kind of element to stop alpha and beta, since it's really dense. So then it will immediately stop these two easily. But for gamma, of course, nothing can stop gamma, so it will just reduce gamma to 10% of its initial value. Okay, just remember, gamma can't be stopped, alpha and beta are stopped. Lead is a dense material that is very strong, that can stop both alpha and beta, but can't stop gamma, but can reduce it. So yeah, just memorize it like this. Okay. Anyways, a charged particle is released as a result of radioactive decay. A, if its speed is 0.06 c and produces... Okay. Now, they're given us speeds, each individual speed, okay? And like we said before, ions per centimeter traveled in air. Okay, this all happens in decay, okay? So, 10 to the power of 5 ion pairs per centimeter traveled in air, then the particle is an alpha particle, okay? Remember, alpha is 10 to the power of 5, and beta is 10 to the power of 3 ion per centimeter traveled in air, and gamma is 10, just 10, no power, okay? That is why alpha has, what's it called, is the best in ionization, while beta is medium and gamma is 0, very bad, okay? So I'm gonna write it like this. A is the greatest one, the greatest power, going down be beta, which is the medium, and gamma is the lowest one, with only 10. Okay? That's it. So memorize it. Hope you understood, and thank you everyone. Wish you the best of luck on your exam. Bye.